Remember in Chapter 1, you learned the concept of sampling error, which was the inevitable discrepancy between sample statistics and population parameters. Remember that you learned that even though the term error is used, it is not a mistake. Researchers know that it's there, and to compensate for it, adjustments are made to formulas. The goal of inferential statistics is to use the limited information from samples to draw general conclusions about populations. The basic assumption of this process is that samples should be representative of the populations from which they come. This assumption poses a special problem for variability, because samples consistently tend to be less variable than their populations. The fact that a sample tends to be less variable than its population means that sample variability gives a biased estimation of population variability. This bias is in the direction of underestimating the population value rather than being right on the mark. Fortunately, this bias in sample variability is consistent and predictable, which means it can be corrected. For example, if the speedometer on your car consistently shows speeds that are 5 miles per hour slower than you are actually going, it doesn't mean that the speedometer is useless. It simply means that you must make an adjustment to the speedometer reading to get an accurate speed. In the same way, we will make an adjustment in the calculation of sample variance. The purpose of the adjustment is to make the resulting value for sample variance an accurate and unbiased representative of the population variance. When we must estimate population variance from sample data to adjust for sampling error, we make a change to the variance formula, which is shown on the slide. The three-step process to calculate the standard deviation is the same, with the exception of the mathematical adjustment we make in step 2. We start out by calculating sum of squares for a sample exactly the same as for a population, except for minor changes in notation. After you compute sum of squares, however, it becomes critical to differentiate between samples and populations. To correct for the bias in sample variability, it is necessary to make an adjustment in the formulas for sample variance and standard deviation. Notice that these sample formulas use n-1 instead of n. This is an adjustment that is necessary to correct for the bias in sample variability. The effect of the adjustment is to increase the value you will obtain. Dividing by a smaller number, n-1 instead of n, produces a larger result and makes sample variance an accurate or unbiased estimator of population variance. Remember that the formulas for sample variance and standard deviation were constructed so that the sample variability would provide a good estimate of population variability. For this reason, the sample variance is often called estimated population variance, and the sample standard deviation is called estimated population standard deviation. When you have only a sample to work with, the sample variance and standard deviation provide the best possible estimates of the population variability. Later in this book, we will use the concept of degrees of freedom in other situations. For now, remember that knowing the sample mean places a restriction on sample variability. Only n-1 of the scores are free to vary, and we call that degrees of freedom equals n-1.